Okay, good morning, everyone. Welcome to the second FHERITALE webinar. So today, I won't spend too much time on the introduction, but welcome to our second webinar on innovation through access, FHERITALE, and the JRC Nanobiotechnology Laboratory. So we have two speakers today. We will first have an introduction to the FHERITALE project from Andrea Rosato, co-coordinator of the project from CIRMMP. And then we will also have Andrea Valsesia from the JRC Nanobiotechnology Lab, VC. So to get us started, Antonio, would you like to share your screen?
Yes.
Perfect, thank you.
Okay, so can I go ahead, John?
Yep, when you're ready.
Yeah. Thank you. Good morning, everyone, and welcome to this FHERITALE webinar, where the main part is the presentation by Andrea, who's going to talk some science and technology in the nano field. And I will just set the ground by telling you quickly a few things about the FHERITALE project. So that's a project in the research infrastructure world, which means it's a consortium of European research infrastructures that are engaged in providing services to the European researchers in different fields. So as you can see from the slide, the consortium is relatively small in terms of infrastructure. We have Instruct-ERIC, which is the infrastructure I belong to personally, and the core business of Instruct-ERIC is structural biology. Then we have the Metro Food infrastructure, who's focused on, of course, as the name and the logo goes, in food science. Then we have the ERIC infrastructure that is based in France, but that's the coordinating body of the infrastructure, whose focus is on environmental sciences. And finally, the fourth infrastructure that is formally a part of the project is IRENE, who is mainly involved on the, let's say, studies involving the exposome. And so the project was put together by these four infrastructures. We are, of course, collaborating with several others that include, for example, Eurobioimaging among the European ERICs, whose focus is on microscopy, at least for the part related to the project. And of course, we have approached many others, and in this process we also got in touch with the JRC, for example. So the overall objective of FHERITALE is to improve the provision of services by European and national research infrastructures, in order with a specific focus on the studied investigation of the impact of artificial materials on life, through taking care of all the dimensions, so health, food, and the environmental impact. And of course, because artificial materials, as you can imagine, is a fairly loose term when it comes down to really narrowing which services which services are available, which services are needed. So we had to prioritize, and our first decision on where to focus the project, and so where to investigate the availability and the need for new services was on plastics. So we are, let's say, dealing with micro and nanoplastics. That, of course, is a very popular subject. And related to that, we have in our scientific priorities bioplastics and plastic additives that are essentially as widespread as micro and nanoplastics of the traditional kind now. And we also have had some, let's say, activities around metals and metal oxides that are very common. For example, titanium dioxide being used as to let's say reinforce the white color in many materials. And because of course it's a small partnership and the scientific remit of the project is very large, we proceed in the project by interacting with numerous external experts, one of these being Andrea. That's how we got in touch to first of all confirm that these scientific priorities are meaningful, and then to, let's say, have their help in shaping our work, which is essentially 2 stages. First of all, and that's been completed already because we are now more than halfway in the project, we mapped all the services available at national and European facilities for the European investigators to study any kind of scientific theme related to the scientific priorities that I just mentioned in the previous slide. And then basically with the map of what's available, we now want to identify which gaps and which needs there are so that we can promote new research and new development in order to facilitate the study of these important scientific priorities by European researchers, which sometimes means you don't necessarily need to have a brand new service or a brand new machine in some place, but you just need to, let's say, refurbish or reshape the offer around current instrumentations in order to enable this kind of studies. But of course we have to ask the community about that. So one of the first major, let's say, products from the project was this landscape of research infrastructures, where we mapped numerous services. The full list is of course very long, and it's available on the project website FHERITALE.eu. And we decided to present a compact view for presentation's sake, and therefore we grouped the available services that we identified already by some broad categories that you see listed there. So we had just about a dozen different categories, and then in each category we have various different services, whereby physical chemical characterization of microplastics can be a number of different things, from defining the shape, defining the size, using lasers versus microscopes versus other tools. And then for each service we know in which facility or facilities it's available, hence you get the dots, the color dots in the rightmost column of the table, where we map which facility is providing which service. So this is, again, in the full table is broken down at the single service level. Now this is more of an overview, and you can see that, for example, physical chemical characterization is relatively broad offered, whereas risk assessment, for example, is in a way lagging behind that. And these, as you see, include both facilities from within the project partnership and facilities, so infrastructures outside the project. And we keep these updated as long as we meet with new people and we add them into this portfolio, let's say. So as I mentioned, and this is my last slide, basically, we are now trying to identify, so that the previous slide showed what's currently available, and now we want to identify what's needed. So with the specific aim to identify gaps that will allow these infrastructures to expand their offer, provide new services, and so they benefit from gaining access to a wider user basis, and European researchers benefit from having a wider availability of relevant services for their research. And that's where also it would be great if you people in the audience could contribute by taking the survey as well. Basically, it asks you what kind of services you would need for your research, keeping in mind, of course, the focus on the priorities that I mentioned before. So micro and nanoplastics, bioplastics, plastic additives, and metals, metal oxides. And I think that's all from my side. So I would just like to thank you for your attention. And if there's any question, I'll be happy to take them. And then leave the floor to Andrea for some more solid science.
Great, thank you, Antonio. Much appreciated. Does anybody have any questions for Antonio? There is the chat and the Q&A, if anybody has any questions. Just while we're waiting there, I'm just going to pop into the chat the link to the survey that Antonio was talking about. This is on the FHERITALE website. So do take a look at that. As Antonio was mentioning, you also have the QR code currently on screen where you can scan and find out information about the survey and about filling in the survey too. Okay, well, if we have no questions for now, like Antonio said, I think we might want to move on to Andrea. So this is Andrea Valsesia from the JRC Nanobiotechnology laboratory. And yeah, and if Andrea, you'd be happy to start sharing, and then we can get on with your talk. Let's just check.
Thank you. Can you hear me?
We can hear you fine. And
can you see the presentation?
We can see it perfectly. Thank you very much.
Okay, thank you very much for the introduction and for inviting me to present this webinar for FHERITALE. My name is Andrea Valsesia. I work for the European Commission, the Joint Research Center, which is located in Ispra, in Italy, northern Italy, close to Milan. And today I will try to present a bit of an overview of our activities, mainly in the characterization of nanomaterials with some examples, for example, on micro nanoplastics, but also other nanomaterials. And at the end of my presentation, I will also try to give some examples of possibilities of collaborations and of open access to our laboratories, to our facilities, that I think that are very useful for the audience. So when we talk about nanomaterials, we are talking about something that is around from many years, and they are studied since many years, but there is still a lot of unknown and a lot of research needs and research gaps that need to be filled. We can classify nanomaterials in different ways. Of course, I like to make these three classes. The engineered nanomaterials, for example, nanoparticles that are added for a technological improvement of a certain product, or nanoformulations, I think all of you have been, or most of you have been vaccinated against COVID in this last generation of mRNA vaccines that are encapsulated in these lipid nanoparticles. So this is a case of engineered nanomaterials that introduce incremental innovation to a certain product. Then we have the incidental nanomaterials, and in this case, these are produced by as byproducts of other processes, for example, condensation or combustion. And I would include nanoplastics in this class of nanomaterials because they are incidentally produced as the degradation of larger plastic debris or microplastics in the environment. So this is mainly an environmental problem that can also be found in other activities and in other sectors. And the third class, which is let's say the most one of the most interesting, but also one of the most dangerous, I would say, is the natural nanomaterials. I mean, if you think that they are natural, they wouldn't be dangerous, but some of them, they are really dangerous. For example, viruses, they are perfect nanomaterials. They have nanometric size. They have very nice structures and architectures. They are super stable, and they can be treated as nanomaterials. So we like to use this holistic view of nanomaterials because we have been encountered them in many different projects, and the techniques that we use to characterize them are almost the same for all of them. So the experience you gain in a certain class of materials can be used for another class of materials. But there is still a strong need of standardized methods and materials. As I said, after 20 years of work, there is still a lot of unknown and poorly understood risks, for example, in toxicity by accumulation. The rich regulatory framework require the detection, the quantification, and the characterization for the risk assessment. And the other problem is that current methods are often expensive, time-consuming, and they often lack of sensitivity. So what is the role of JRC nanomaterials regulation? We support directly the regulatory agencies. So we have a lot of interactions with ECA, EFSA, or EMA for their dossiers, for their files. Very important activity that is not done here in ISPRA, but in Geel, in Belgium, by another JRC site, is to develop and produce and distribute reference materials. And reference materials are very important for the accurate application of different analytical techniques, and in particular for nanomaterials. Then we support directly the legislation. So, for example, we participated to the writing of the recent regulation for the microplastics in drinking water. So we directly write the regulation, or directly support the writing of the regulation. We participate and contribute to international standardization bodies, OECD, ISO, and so on. But also we do some pre-normative research. And I would put in this box also all the projects we are doing with our customers in the frame of the Open Lab project. I will show you at the end of the presentation what are the opportunities. What are our laboratories? The JRC Nanobiotechnology Lab. Actually, we have a state-of-art facility for very interdisciplinary studies with a special emphasis on the characterization of nanomaterials. As infrastructures, we have a clean room facility, ISO 6 and ISO 7. We have a biology lab, we have a chemistry lab, and a PhysChem characterization lab. And we are a team of about 20 scientists with a very knowledges. Instrumentation and techniques. This is the, let's say, the standard techniques we have available. One of the uniqueness of our laboratory is that we have available all these technologies in one single laboratory, so you don't have to search for other technologies, for example, as in a university campus or in other facilities. We have all these group of technologies available in our labs. We have many more instruments than the one presented here, but just to make you some examples, we have separation and characterization of nanomaterials when they are dispersed in liquids. So, for example, analytical ultracentrifuge. We just bought a new one, and it will be available next year. Field fractionation, ICP-MS, and a lot of different optical detection techniques and characterization techniques. Then we have techniques for material characterization and surface analysis, X-ray diffraction, micro Fourier transform, confocal Raman, TOF SIMS and XPS, which is a quite interesting facility as well. And then we have electron microscopy, focused ion beam, SEM, and TEM with ADX and cryo-TEM with a sample preparation facility. So we have quite a good range of techniques that could be used for different applications, in particular for the characterization of nanomaterials. Today, I would like to focus a bit on what is my expertise on the optical methods, so how to develop and why developing optical methods for the characterization of nanomaterials. There are many different advantages of using optical methods. I would name them. For example, optical methods are usually low, they consume low energy, for example, with the introduction of the new light sources, for example, LEDs, or otherwise they are usually amenable to automatization. They are compatible with remote sensing. They are, for all these reasons, they are low cost, so they are easy to integrate in other technologies, because we have always to remind that when we participate to the writing of a regulation, or we give our suggestion, we have to take into account that then this methods needs to be used on the field by routinely, so the cost and the economic impact of these methods or this routine surveillance need to be affordable. These methods are developed often for high-end technologies, for example, in the space or military science. So they are very fancy and advanced technologies. And then one of the last introduction in the last years is the use of machine learning, for example, for image recognition and spectral identification, which makes these technologies even more interesting. What is the big, let's say, trouble for these methods, if we compare them, for example, to electron microscopy, is the lack of resolution. So there is the common idea that optical microscopy is not suitable for the characterization and identification of nanomaterials because the lack of resolution for the diffraction limit, for example. So in the last years, there were a lot of different technologies that can overcome this limit by super resolution. There are many different approaches. Some of them, they are based on the light scattering methods, and this is something I will show you today. So how we can overcome the resolution limits using optical microscopy to detect and characterize nanomaterials. Here, an example of an hyperspectral enhanced dark field microscope, where we have a special dark field condenser. So there is a white light source. Then there are different options in this setup. This is a very classical setup. The dark field condenser concentrates the light beam in a cone and in a little point on my specimen, on my sample. Then if the specimen is transparent, for example, a glass slide, the light beam passes through and is not collected by the objective lens, so I see dark. But if there is a little particle there, and for little particle, I mean a very small particle of even smaller than 100 nanometers, this particle scatters the light, and this light can be collected by the objective lens. Of course, if I'm using a white light source, this light can be dispersed and can be measured the spectrum of the scattering of this light, and this is often, or it is related to the size and the refractive index of the material. So I have means of characterizing the size of the material at a single particle level, but also its composition by the detection of the refractive index. And then the idea is that I can use this together with an imaging system and to create a spectrum for each pixel, so to create hyperspectral imaging. This is very convenient because I can obtain a lot of information from the same field of view. The physical effect is called light scattering, then is classified in different ways. When the particle size is much smaller than the wavelength, we are talking about the Rayleigh scattering. When the particle size is smaller than the wavelength, and we are talking about the wavelength of the visible light, we are talking about the Mie scattering, and then there is also Mie scattering from larger particles. We also developed new approaches to exploit the light scattering. I'm not going into detail of this microscope. I'm just showing the results we could obtain. So in this case, we are obtaining the light scattering from particles with hyperspectral imaging by using the interference that these particles are creating on top of the glass slide, on top of the specimen, and we are collecting basically the scattered light. What you obtain is a contrasted image that is able to see and to detect very small particles. For example, particles well below 1 micron, so it's able to detect nanomaterials and to also identify their refractive index. For this technology, we have different applications, for example, for material characterization, for detection of nanoparticles, nanocontaminants, for example, nanoplastics in different matrices. But we are trying to apply it also for the super resolution of living cells. So it's easy, let's say, to couple to this microscope, which is an inverted microscope, live cells incubators. So you can grow your cells in a medium with a very controlled environment, and then you can use this microscope to monitor how the cells behave in real time, but also you can also monitor if you add some nanomaterials, how these nanomaterials are interacting with the cells and how they are influenced by the presence of the nanomaterial. Here I just show you a recent experiment we did with macrophages that were growth on a glass slide in good biological conditions, and then they were exposed to polystyrene beads of the size of 200 nanometers. So you can see here in this frame, this is the starting frame, a macrophage. We can monitor many of them. So we can see the presence of the different organelles, for example, the lysosomes and the cell membrane, and we can monitor it in real time. Then I will try to I will try to use my pointer, to start the video. Okay, so as you can see, this is a video that has been taken for around 12 hours. So each frame is 7 minutes. So this image is super accelerated. So you can see that we can monitor in real time all the movements inside the cells of the organelles. You can see very well the external membrane. And then we can also see when the nanoparticles, you can see here the little yellow arrow, when the nanoparticles are hitting the cell membrane and how the cell membrane is reacting. So I can maybe show it another time. So you can see that the nanoparticles arrives and they are interacting with the membrane, and sometimes they produce a bit of turbulence in the membrane, and then they are most probably uptaken by the cell. So this is quite powerful technology that we developed. I have to say that this is a very, let's say, very inexpensive optical setup that produces quite powerful results. If we go back to the more, let's say, standard setup for the hyperspectral enhanced dark field microscopy, this is the setup we have in our lab. So we use as a structure standard optical microscope, as I mentioned before, using this special immersion oil condenser. So here you have the sensing chip. Then the objective collects the light, and then the spectrum is made by using a tunable filter. So basically, you can obtain hyperspectral images with a resolution of in spectrum of 5 nanometers, with a typical acquisition time of around 30 seconds per image. So it means that it's pretty fast. What is the resolution in size for the particles? As you know, inorganic and metallic particles scatters the light more than the other particles. So we can detect very small noble metal particles, for example, gold and silver, down to 10 nanometers. We can detect polymeric nanoparticles like polystyrene and other nanoplastics at the size of 50 nanometers, and liposomes or lipid nanoparticles with the size of 80 nanometers. So we are perfectly in the nanomaterial characterization range. Just to show you what is the size resolution, we took, of course, polystyrene beads as a calibrant. As you can see, we can see single nanoplastic particles down to 50 nanometers. Of course, the scattering cross-section is proportional to the size of the particles. So the more the particles the bigger the particle, the higher the scattering intensity. And we can detect them up to 1 micron. Then we will fall out from the mere scattering regime, and we won't see the scattering cross-section proportional to the size and the refractive index of the material. How we can use this technology? Actually, we like to call it a high content, because you collect a lot of information using the hyperspectral images, but also is a multi-measurement technique. For example, if you couple this technology of tracking of the nanoparticles with functionalized surfaces, you can also monitor in real time the binding of nanomaterials to different collectors. For example, this enables the surface characterization of the nanomaterials via their affinity to these different collectors. And we developed these methods in particular for the characterization of the hydrophobicity of nanomaterials, which is one of the parameters that was not possible to measure until a few years ago, because there were no methods. So using this method, we introduced this opportunity, and we also went for the standardization. And now the method is a test guideline at the OECD that has been adopted in 2023. So you can download it from the OECD website. You can try to reproduce it in your lab, or it can give you also support. This is some of the services we give in the context of our open access facilities. How we can determine the hydrophobicity index? So we have basically two collectors. One collector is a hydrophobic collector, and another collector is a collector that has an opposite charge compared to the charge of the nanomaterial that you have to characterize. So when the particles meet the opposite charge collector, they bind to the collector at the maximum binding velocity because they have no energy barrier, so they just stick to the collector with a high speed. What happens when they meet the hydrophobic collector? If the energy barrier is still there, but if the particle is hydrophobic enough, or it has a residual hydrophobicity, even if it's dispersed in water, it can overcome this energy barrier and it can stick to the hydrophobic collector. So we measure the hydrophobicity index. We define it as the logarithm of the ratio between the velocity of binding on the hydrophobic collector divided by the maximum binding. So it means that if the binding on the hydrophobic collector is relatively high, this will produce an hydrophobicity index which is close to 0. If the velocity is very small or even 0, it will produce a hydrophobicity index which is smaller than -1. So with these parameters, we can quantify the hydrophobicity of nanomaterials with a very simple system, a standardized system that can tell you if the nanomaterial is still hydrophobic. And this has influences in its toxicity. We apply this approach, for example, to characterize chemically aged micro and nanoplastics. These particles are produced by our colleagues in Geel, in Belgium. So basically, they start from polyethylene and polyethylene terephthalate foils. They cryomill them to produce the micro and the nanoparticles, and then they treat them by potassium hydroxide to mimic their aging. Basically, they produce oxidation. So the more the exposure time to the potassium hydroxide, the more oxidized are the particles and the more dispersible in water because the starting materials are hydrophobic. So our colleagues, they wanted to see if there were a difference between the aged and not aged nanoplastics. And actually, we could measure them very well with our technique. So as you can see, the pristine PET has a very low, close to 0 hydrophobicity index, which means that it's hydrophobic as well, the pristine PE. But when you work with the aged PET, the oxidized PET, you can see that the hydrophobicity index is similar to the one of hydrophilic polystyrene beads, for example. So this means that we can quantify also this difference. Now we are working with them in trying to produce a tuned hydrophobicity of these particles because the hydrophobicity index depends on the exposure time to this oxidation solution. Then another example to identify PET nanoplastics in tap water. As I said, with the hyperspectral imaging system, you get a scattering spectrum for each nanoparticle that sticks on your chip, and this scattering spectrum is related to the size and to the refractive index of the material. So you have a way to, if you know, for example, the size, you have a way to characterize the refractive index of the material. So you can distinguish between, for example, a nanoplastic particle or inorganic particle. And we apply this approach for the identification of PET nanoplastics in tap water. We used the tap water from our laboratory, which is pretty dirty, so it was full of different particles. As you can see, once they are immobilized on the collector, we can get the scattering spectrum for each particle. So you can observe that there are some particles that are high Mie scatterers, and other particles that are big, but they are low Mie scatterers. So these informations are very important. And basically, the small particles which are scattering a lot of light, they are nanoplastics compared to the other particles present in the water. So this is the physical reason why we can distinguish them. Then this is a bit of the process. We, of course, applied machine learning, but also you can use an analytical principal component analysis to distinguish the spectra, to identify the spectra of the PET particles, and to quantify the concentration in the water. So this is was our experimental approach. So we created a reference. Of course, you need to create a reference of your particles that you want to measure. We did a dispersion of polyethylene terephthalate in particles in ultra-pure water. We created different fractions because, as I said, we need to work with a monodispersed sample, because the scattering depends on the size and the refractive index. In this case, we want to measure the refractive index. So we created these 7 fractions with more or less 100 nanometers in size, from 1 micron down to 100 nanometers. So we created these fractions and we collected the scattering spectrum, the scattering spectra of the particles for each spectrum, and we created some statistics. Then we did the same with the matrix, which is the tap water. Of course, this tap water has been concentrated, like 5 liters were concentrated in 50 mLs. So all the particles are really concentrated in these samples. And we created the same fractions. And then the sample, which is the reference, spiked in the matrix, and to see if the system is able to detect and count only the PET nanoparticles. So this is how the results. These are the average spectra for the different fractions of the PET in ultra-pure water. As you can see, the large fraction, close to 1 micron, F1, has a high scattering intensity with this spectra here. And then the smaller the size, the smaller the scattering intensity. And here are all the spectra we collected for the PET in ultra-pure water. These are the spectra for the same fractions, but of the tap water particles alone. As you can see, those are distinguishable at least in terms of their intensity, but also on their shape of the spectra. And then we provided we trained the system with the spectra to recognize to which class the 2 particles belongs. And then we use this AI tool to identify the PET particles in the tap water. As you can see, we can count in each sample for each fraction the PET particles and count the particles of the background, which is quite interesting with a relatively simple system. Then, as a second example, let's say in the frame of talking about let's say an holistic view of nanomaterials, we apply the same approach for the detection and the identification of viruses in air. As you know, this is a very hot topic because after the COVID, there were a strong demand of methods for the continuous monitoring of air quality, in particular for preventing the spreading of diseases and airborne pathogens. The problem is that the air collection and the identification or the quantification of pathogens cannot be made on the same system at the moment. There are different technologies that are trying to overcome this limitation. Basically, you have to take your air sample, then go to the lab and do basically PCR quantification. So this takes a lot of work, a lot of time, so it's not compatible with affordable monitoring systems. A couple of years ago, we did a technology screening of what was around, and basically we created this map, which is the combination between the different sampling technologies and the different identification and quantification technologies. Of course, a digital PCR remains the golden standard, but there are two classes of methods that could be very interesting because they could be used for continuous air monitoring. Those two classes are the direct identification through the physical chemical properties of nanoparticles, and then the use of biosensors. The problem is that they are good candidates for surveillance, but they can be used in real time. They are sweet, they are autonomous, field deployable. And why? Because, as I mentioned in the beginning, they are based on mainly on optical methods. Another important aspect of this problem is that the specificity is not always a plus, but most of the researchers that are looking at the monitoring the development of epidemics and pandemics, and they want to do some surveillance. For example, the Italian Institute Lazzaro Spallanzani, that they are dealing with the epidemics and pandemics on the Italian territory. When discussing with them, they like to see when they have a positive case, not the specific virus, because sometimes this pathogen is mutating, so it's not possible to detect it with digital PCR, but they want to see the family that this virus belongs to. So it is important to develop methods that are really broad in terms of identifying, yes, this is a pathogen, this is a virus that belongs to this family, but not to be so specific at this stage. So the idea is to use the scattering technique, the light scattering technique that I showed before, the dark field hyperspectral, to see if the scattering, the light scattering properties of different families of the most common respiratory pathogens can distinguish these particles in families. And then, since we didn't have access to these particles as samples, as you can imagine, this is not easy to find. We decided to start from the high resolution electron microscopy images, and we found a very nice database of electron microscopy images of the different families of the respiratory viruses produced by the Robert Koch Institute. And you can see that the adeno and the corona and the orthomyxon and paramyxon, these are the four main families. They have very different shapes and size, and we wanted to see if we can distinguish them. So it seems that from the electron microscopy images, we can distinguish them. So we used the electron microscopy images to create particle models to simulate the scattering spectra for the different particles. So we made a quantitative morphological analysis, and you can see that the different families, for example, by the area and by the circularity, so their shape, they are distinguishable, and we can use the same spectra. I mean, they will produce different scattering spectra that they will be able to identify them in terms of family. So this is a quite interesting approach. So actually, when we start by knowing the shape of a particle, a virus particle, we have two ways. One is the one I just showed, so you can create masking and modeling and to calculate the mean scattering to see if I can distinguish them. But the first approach could be also to try to create a proxy of this particle, for example, using virus-like particles to actually measure the scattering spectrum of these particles. And this is what we did in this project. So we created a set of different viral particles and other particles, and we measured the scattering cross sections in a similar way as we did for the PET in the tap water. As you can see, we have different virus-like particles and other particles, and you can see that the intensity, the scattering intensity, for example, of the polystyrene 200 and the H1N1 VLP or the SARS VLP are completely different, for example, compared to the scattering spectra of the norovirus and the dengue virus. So there is a way to distinguish these viruses in these viral particles in terms of their scattering spectra. There is a very good correspondence between the measured and the simulated MIA scattering spectra for these particles. So there is a very good correlation. So the particles scattering can be either measured or simulated, which is a very great advantage. So we did exactly the same approach that we did for the nanoplastics in water. So we trained a machine learning system to recognize the different virus-like particles and the different among the other particles. So these are the PCA categories, let's say. It is possible to distinguish the classes. Of course, there are some overlaps, so you have to bear in mind that we are not working with high resolution spectra like the Raman spectra or the Fourier transform infrared spectra, but we have this scattering spectra which are not extremely resolved, but actually they enable to distinguish the particles. And then this is evidenced by these confusion matrices with these two different algorithms, the random forest and the neural network. And as you can see, with both the algorithm, we can distinguish, the system is able to distinguish the different VLPs among the other materials with a very good level of confidence. Say that one of the lowest is 20% because it is really low represented, but we have also more than 97% in the case of nanosilica. So we said, why don't using this approach to detect coronavirus in air? So we did some air sampling campaign in the gardery where there are kids after school here at the JRC in our campus. So we collected the different air samples when the kids were in or when the kids were not in to create some negative samples. Some blanks, basically. We use this aerosol sampler, which is provided by Aerosol Devices. It's a special aerosol sampler that is able to efficiently, with more than 80% of efficiency, to collect very small particles like viruses are. And then we made the analysis in our lab using our system. Of course, we couldn't find we couldn't find SARS-CoV-2 samples using viruses using the digital PCR in the samples, but we used the same negative pool samples, so our blanks, to spike them with SARS-CoV-2 to make a calibration curve. And as you can see, we could determine the concentration of SARS-CoV-2 using our machine learning based optical method. And we compared it, we calibrated it with the determination by the digital PCR. And there is a good agreement between the two technologies, which means that our approach is relatively, let's say, that is relatively simple and can be used on field. It's really promising. As you can see also in the positive sample where the kids were in, we could find some particles here that they have the same scattering, let's say, properties than the spiked SARS-CoV-2. That means that those particles could be other viruses belonging to the same family, maybe not the SARS-CoV-2, but this is an indication that we can determine the presence of viruses in air using this technology. And this is the final goal of this project, is to deploy the reading system on the field, to couple it with the sampling system that in a reasonable amount of time, let's say less than 30 minutes, can calculate the concentration of these potential viral particles in air, and in a completely autonomous way. Then it is possible also to store the sample to perform the digital PCR afterwards, for example, the day after or the week after the sampling. Then I have a few slides on the open access. I don't know if maybe I ran out of time, but very quickly, all these technologies, the one I showed you, the super resolution microscope for the cell monitoring, the measurement for the hydrophobicity index, the characterization of nanoplastics in water or in other matrices are offered in our open access program. So we had already quite good examples of different samples we measure with these techniques. And we have different ways to offer this open access. We have our own open access research program to the JRC research infrastructure. Typically, these are 5 to 10 days projects free of charge. There is around 1 call per year of this open access JRC, but then we are also inside big, let's say, distributed research infrastructure programs like CERIC. These are more, let's say, a bit larger projects from 5 to 20 days, but then we have also even larger projects that could last 2 years. Then we are inside the NFFA research infrastructure. And then we have also other ways to make very or much longer collaborations with our customers. For example, we have a collaborative doctoral partnership program. I think the next call will be out at the end of January next year. In this case, we host a PhD student that is co-financed by the JRC and the let's say home university. And then we also offer training and capacity building. Now the call has just closed in October, and we will organize the next training and capacity building in March here in ISPRA on specific topics, mainly for the characterization and identification of nanomaterials. So the goals are to enhance dissemination, to boost the competitiveness in Europe, and to bridge the gap between research and industry. I have to say that we really love to work on these projects because our customers, they bring very fancy samples, very different problems that they have to solve, and it's super exciting to try to solve their problems using our technological approaches. Some figures, maybe I can skip this. We have quite a long history now since 2017 of the open access. The topics, actually, these are the priorities that we set. Characterization of micro nanoplastics, characterization of advanced materials. So it's the first category I was mentioning in my first slide. and then the characterization of liposomes-based products, nanoparticles, and lipid nanoparticles, and so on. This is I can skip as well, and I just would like you to mention what we will do in the next training and capacity building. We received really a lot of requests, more than 80 requests. We have like 25 spots available, so we will need to make a good selection. And as well, this training and capacity building is organized in our, let's say, hot topics. One is the nanoplastics as well. So with the students here, we will make a case study of nanoplastics dispersed, for example, in food or in the drinking water. So we will do together with them the development of analytical techniques to detect these particles. Then the second topic is the detection and characterization of innovative nanomaterials in food. The third topic is the hands-on training on synthesis of nanomedicines, including liposomal drug products. And then this year we introduced also hands-on training on 3D bioprinting, which is a very interesting approach to develop new methods for assessing nanotoxicity. And I think, yeah, this was the last call. Now is closed. So please have a look to our webpage, where we are regularly publishing our calls. So you can scan this QR code. And I think this was my last slide. Sorry if I were a bit long. And this is the credits of the people who worked in the results I presented in my slides. And thank you, and I would be happy to take your questions.
Okay, thank you very much, Andrea. That was great. Yeah, I mean, time-wise, I think we have time for one quick question. We have one in the chat, actually, from Monica. And the question is it possible to measure the hydrophobicity of microgels or Janus particles using this technique? This is when, yeah.
Of microgels?
Yes.
Can I interrupt my sharing the screen, or? Yes, if the microgel is dispersed in water, we can use the same approach, because what we are doing is to count the particles that are immobilized on the different collectors in real time for a time frame of around 20 minutes. So we count the particles, and then we we calculate this hydrophobicity index. So if the particles are dispersed in water, we can use this technique without any problem.
Okay.
If they are micro, maybe they are a bit big for this technology, we can use simply bright field technology if the particles are relatively big, let's say a few microns. So this dark field and enhanced dark field is to characterize nanomaterials.
Okay. Well, I think that's where we are with time, unless there are any other questions, but I do not see them. So in that case, I think we can, thank Andrea and also to Antonio for a great webinar. And the recording of the webinar will be made available soon. And please keep in the loop with FHERITALE on our website and our social media for the next webinars. And thank you to everyone for your attendance. Okay.
Thank
Much
you.
appreciated, everyone. Thank you.